Okay, so this is on WireGuard, which is a layer 3 tunnel that lives in the Linux kernel. First, I come from a little bit of a different background than probably many of you here. I come from an offensive security perspective. And so my background is in exploitation and in breaking kernels, breaking networks. And as part of that, I work on rootkits and other offensive security software. And a big part of that was making a good exfiltration method. But I found in doing that a lot of the same methods from making exfiltration methods could be useful for making secure tunnels for a defensive perspective. Additionally, in looking at tons of vulnerabilities over the years and breaking these systems, I've seen a lot of patterns of just what goes wrong in code. And so I tried to make an overall design that would lead itself to safe coding patterns. So that's the impetus of WireGuard. So as I said, it's a layer 3 secure networking tunnel, and it's opinionated. It's not layer 2, because I don't think layer 2 network tunnels are the way you should make your network. And as we'll see, there are a lot of choices that I've made for you where you should do it this way because it leads to a better security design in general without an option. So it's layer 3, lives in the Linux kernel, so it's really fast, but there are people working on cross-platform user space versions as well. It's UDP-based, and it gets through firewalls pretty well, nice hole-punching characteristics. I tried to use modern crypto, but also conservative crypto, nothing too newfangled, so we'll go into that. And the emphasis, as I said, is on being very simple and very auditable, so that you can actually look at this and realize it's good, secure code. The authentication model is a bit like SSH's authenticated keys. Rather than having certificates or some complicated key exchange, you simply pre-exchange public keys like you would with SSH, and then two peers can talk to each other. So in other words, the key distribution problem, we don't handle. That's left better for other layers, for other things you could build on top of it. So instead, we implement something very simple, like SSH's authorized keys that then you can build on top of. And it's meant in general to be a replacement for OpenVPN and IPsec. So just to put this in perspective, OpenVPN is 116,000 lines of code, plus all of OpenSSL. The Linux XFRM layer for IPsec is 13,000 lines of code, plus Strong Swan, which is 405,000 lines of code. Soft Ether is 329,000 lines of code, and then WireGuard is less than 4,000 lines of code, so enormously smaller. So to put it in the solar system of VPNs, we're Pluto all the way out there. So we have a very simple network interface. We don't have complicated transform tables like IPsec. We just have a network interface that you can add and use just like any other network interface on Linux. In this case, WG0 for WireGuard, and it works just the same way as ETH0 or WLAN0. And all your favorite sysadmin tools work fine with it. So there's nothing new to learn in the interface, simple thing you've been using forever. But WireGuard is also blasphemous in choosing that kind of thing. We break the layering assumptions that came out of the 90s and went into IPsec. IPsec has a nice transformation table that exists at a different level than the network interface for encrypting packets. The keying daemon is a separate thing from the transport data encryption. And IPsec is very academically perfect. But it leads to this enormous bloat and possibility to implement and possibility to configure. And so we just do away with the layering, which is wrong in a lot of ways. But we start from this contradiction where what if we just get rid of the layering, make it all a network interface, and then we try and come up with interesting crypto solutions and interesting engineering solutions to work around the contradiction. So the the fundamental thing that makes this possible is what's called crypto key routing, where we have a relationship between a public key and an IP address. So each WireGuard interface has its private key, it has a listening UDP port, and it has a list of peers. Each peer is identified by its public key, and it has a list of associated tunnel IPs, a list of IP addresses that peer identified by its public key is allowed to be inside of the tunnel. And of course, it optionally has the endpoint IP and port of another peer that it's talking to. So we additionally don't want any daemon or anything complicated running to make it work. So it appears stateless to the system administrator. You set it up, and then it just works. You add an interface, you configure its peers, and then packets can just be sent. But of course, you can't have a solid protocol that's secure while actually being stateless. This is a contradiction. So as we'll see later, we have some nice tricks to make it appear stateless to the administrator, while underneath we're doing the rest. Endpoints roam like in Mosh, so you can put your laptop to sleep on one network, open it up on the other, and then packets just flow and work as you would expect. No need to reconnect. And as we said before, the identities are just static public keys, short, base 64, it's 44 characters. You copy and paste it around, put an email, any type of key distribution you want to do. And everything else is invisible to the admin. So we accomplish this with a series of timers. And the way we developed these timers was it's an event-based timer mechanism, and we mapped out every transition of state within the timers so that there are no undefined transitions. Worked out the whole matrix. So we're not going to hit any corners. So the basics boil down to this. User space sends a packet. If there's no current session in the last 2 minutes, then we send a handshake initiation packet to start a new session. If we don't get any handshake response after 5 seconds, we send another handshake initiation. Every time we get a successfully authenticated incoming packet, if we don't have anything to reply after 10 seconds, then we just send an empty authenticated packet. This means that if we don't get any successfully authenticated incoming packet after 15 seconds, we know something must have happened, and we can just reinitiate the handshake. We have a lot of defensive coding and defensive structures to make sure this can be implemented safely. All state that's required is allocated during config. We don't have any malloc bugs because we don't really need malloc. So that this eliminates a whole class of vulnerabilities. All packet headers have fixed width fields, so there's no parsing. This is awesome. No parser vulns. Who would have thought? So simplest way to eliminate a whole class of vulnerabilities. Then the last one is a little more difficult to implement. We don't modify any state in response to an unauthenticated packet. Only authenticated packets can modify state, and only a particular amount of state. So this eliminates a whole other class of unauthenticated remote vulnerabilities. As I mentioned, this grew out of a rootkit project, and so being stealthy is super important. We don't want WireGuard to respond to any unauthenticated packets. It should be completely silent unless it's talking to a legitimate peer. This completely hinders scanners and service discovery. All the Z mapping stuff will never find anything in WireGuard because it just won't be able to find the existence of WireGuard endpoints. And so the service only responds to packets that have correct crypto. It's also not chatty, so when there's nothing to be sending through the tunnel, it just goes to sleep and stops sending anything. So how do we make this work? First of all, we use Trevor Perrin's noise protocol framework, developed with a lot of of feedback from the WireGuard development, and we have a custom implementation of this, of NoiseIK for the kernel. Has a number of nice properties. We have perfect word secrecy. There's a new session every 2 minutes. We avoid key compromise impersonation. There's identity hiding, so we never actually transmit a public key in the clear over the wire. Of course, we use authenticated encryption as nice replay detection, but that still allows for packet reordering because networks will reorder packets, and as we're using UDP, this is a real issue. And we use modern primitives. Curve2519, Blake2S, Chat220, Ploy135, Sipatch24, the DJB cipher suite. And importantly, there's no cipher agility. This might be controversial, but really cipher agility was this terrible idea of the 90s. So we don't have any downgrade attacks. If there's ever a problem with these primitives, then the software will be updated, and you'll update to the new software, and you won't mix on your network insecure way in with the secure way, because that's clearly a terrible idea to mix your secure elements with your insecure elements. So there's no cipher agility. If it breaks, you upgrade. That's it. So the key exchange is one round trip. There's initiator to responder, responder back to initiator. They both calculate their symmetric session keys, and then they can start exchanging transport data. Okay, so we want in the handshake to preserve all these principles of guarded state and fixed length headers. And we also want both sides to be symmetric. We don't want there to be a server-client role. We want either side to be able to reinitiate a handshake at any time, so they can swap roles. And of course, invalid handshake messages need to be ignored so we can keep our stealth principle. So each peer has their static identity, long-term public key. This is what's exchanged in the SSH authorized keys-like way. And the session keys are derived from a series of ECDH operations. We have ephemeral static, static ephemeral, and ephemeral ephemeral. These make up the so-called triple Diffie-Hellman that might be familiar to some of you from the Signal protocol. But because we want this to be one round trip, we additionally have a static-static Diffie-Hellman in the first message, which is almost always a bad idea if you don't do it right because it allows for replay attack. So we have some nice ways of getting around that with monotonic counters. So it's just one round trip, and it's super simple to implement in practice. Kernel code is usually a little bit more verbose and ugly, but even so, it's 441 lines of code for a key exchange. Compare that to the massive IKE daemons like Swan. And you'll notice we don't have any certificates. There's no X509 or ASN1 parser that we're adding to the kernel, thank God. We just have these very simple public keys you paste around. And if you want, you can then build on top of this, say using TLS or LDAP or any other terrible things you want to use. You can build a whole certificate mechanism on top. But WireGuard just provides the basic building block underneath from which you can build a secure system. There's also poor man's post-quantum resistance. There are a lot of nice post-quantum things out there, but they're new, and we're trying to be conservative, so we don't use them. Instead, there's optionally the ability to add a pre-shared symmetric key. Because of Grover's algorithm, 256-bit symmetric key can be brute forced with a quantum computer in the time it would take for a 128-bit symmetric key. And it's actually been proved that Grover's algorithm is an optimal speedup. So we choose big symmetric key like 256-bit, and then because the complexity then goes to 128, we know we'll be safe even post-quantum. But of course, pre-shared keys are easy to steal. Key distribution is even worse with pre-shared keys. And so it only augments the ordinary handshake. It doesn't replace it. And the idea here is that if an adversary is recording all the traffic from now in hopes that in 10, 20, 50 years, they'll be able to decrypt it all, Hopefully by then, the pre-shared keys will have disappeared from rusty hard drives. That by the time we get quantum computers, the pre-shared keys will have been lost. So in case there is bad key distribution with them, it's still better than it otherwise would have been for decrypting past traffic. There's denial of service resistance, especially important in a one round-trip handshake. Hashing and symmetric crypto is really fast, but pubkey crypto is slow, and even Curve 25519, which is really fast, holds all these speed records, it's still slower than what an ordinary network can do. And so you can overwhelm a machine by asking it to do Diffie-Hellman operations. OpenVPN and a lot of OpenSSL versions, this is still an active denial of service attack. And UDP makes this especially difficult because we don't have immediate IP address attribution. You can spoof packets. So WireGuard uses cookies to solve this. So we'll go through a small history of the cookie idea. TCP-like cookies has a dialogue where initiator says, OK, compute this Diffie-Hellman. Responder says, your magic word is Carmen Sandiego. Ask me again with the magic word. Initiator says, my magic word is Carmen Sandiego. Now will you do it? And so because there's been this round trip, there is IP address attribution. So this proves IP ownership, but the only way then you can rate limit on the IP is by storing the association between Carmen Sandiego and that IP. So now we need dynamic allocations, and this doesn't work for us. And this also always responds to messages, so we violate our stealth principle. And of course, the magic word itself can be intercepted. So this is not a robust solution. Next, we have cookies that are like DTLS or IKEv2, which is a little bit more clever. Instead of Carmen Sandiego being the magic word is some hash, where the hash is from a PRF, where the key is some responder secret that's changing, and the initiator's IP address. So now you don't have to store state. You don't have to have a stored association between the magic word and the IP address because you can just compute the same MAC and confirm that way. But again, we have the issue where this always responds to the message, so we lose our stealth principle. And again, the magic word can be intercepted, and the initiator himself can actually be denial of service attacked by flooding the initiator with fake magic words. A couple major vulnerabilities in DTLS and IKEv2. As an aside, a little bit different, there's the proof of work. Compute this Diffie-Hellman. Responder says, well, mine a Bitcoin first, then ask me. Initiator says, I toiled away, I found a Bitcoin, now will you compute the Diffie-Hellman? So this is great if the puzzle is harder than the ECDH operation. In fact, it's perfect. But because we want the roles of initiator and responder to be symmetric, and we want them to be able to switch sides, there's a DOS potential because of the anti-DOS technique where, say you have a server that has tons of peers, if it has to complete all these proofs of work for all these peers, it's not going to scale well. So the WireGuard variant builds on top of the DTLS and IKEv2 variant. Each handshake message has two MACs, MAC1, MAC2. And MAC1 is calculated as a hash of the responder's public key and the handshake message. So if the MAC is invalid or missing, then the message is completely ignored. If it's there, then it means that the initiator knows the identity of the responder a priori. In other words, you can't scan for this if you don't already know who you're scanning for. So we maintain our stealth principle. If we're using pre-shared key mode, then we can make it slightly better by using a PRF instead of a hash function where the key is the pre-shared key. But the security model should be analyzed in terms of the lesser case of only the hash. If the responder is not under load, then it proceeds normally. We don't care about MAC2. If it is under load, that is, if it is experiencing a denial of service attack, if its queues are full, then we respond with a cookie reply message, where the cookie reply message isn't a cookie in clear text. Rather, we take the same type of cookie from DTLS and IKEv2, where we take the MAC using responder secret of the initiator's IP address, and we encrypt it using as a key some hash of the responder's public key, so that only then the initiator can read this cookie reply if it knows who it was talking to in the first place. And importantly, we set as the additional authenticated data the contents of the handshake message that provoked this. So in this way, we bind the cookie to the original message so that you can't then send fake magic words back to the initiator. And of course, if we're using PSK mode, the key is a little bit bigger. Then the MAC2 is just a simple PRF, the handshake message, using the cookie as the key. So then once we have IP address attribution, we can just use ordinary token bucket rate limiting. We maintain stealthiness. Cookies can't be intercepted. Initiator can't be denial of service attacked. Okay, we're running a little low on time, so I'll speed through the rest. Performance-wise, we're in kernel space. We're not a ton tap driver. We're not like OpenVPN or something. So it's really fast. We don't need to copy packets. And we're using chop poly, which is fast on all hardware. AES-NI is really fast too. But in fact, as instruction sets have these vector instructions that get wider and wider, chop poly is becoming even faster than AES-NI because it vectorizes so well. And it can be implemented in a side channel attack free way on pretty much all general purpose processors, unlike AES. And in general, the simple design of WireGuard leads to better performance. Less code equals a faster program? Not always, but when we're talking 4,000 lines of code versus 400,000 lines of code, I think in this case, there's an argument to be made just about the simplicity. And when we look at the measurements, indeed, WireGuard beats the competition on latency and on throughput. So just to recap, it's less than 4,000 lines of code. We've got the crypto key routing, which associates a public key with an IP. We just have a standard network device, secure coding patterns, minimal state is kept. It's super stealthy. We have a modern handshake, DOS mitigation, and it's really fast. So you can learn more from wireguard.io. This is not just an academic proof of concept. This is real production code. We're looking at mainline inclusion in the Linux kernel as our goal for this year. There's a mailing list, website. Thanks a lot. Open it to questions. Yes, so the nonce in each transport message doubles as a sequence number. And we have something of a bitmap where we keep track of previous received packets and a nice bit shift so that it rolls over. So you can get out of order packets up to a certain amount from before.
You mentioned the focus on simplicity. Have you considered applying formal verification techniques to that protocol?
Yeah, so actually I'm looking into that now. First thing to do is to prove the handshake. And then the next thing to do will be make some super secure verified implementation in Haskell or some other language. In fact, people are looking at Rust for this too. But yeah, certainly first step would be trying to prove the handshake.
So, caveat, I've been following IPsec since it was a BOP in the IPF. And I agree that it's complex, but partly my personal perspective has always been its implementations that made it so complex. A couple of points and just a question also. So, it's network interface based, right? And so you don't have the concept of traffic selectors, which means that the assumption is that everything going to have that interface will then be encrypted.
That's right. So this is a nice thing where if it comes from the WireGuard interface and it's from the IP address that a certain peer is allowed to use, then you know it's you know it's private, and you know that it's authentically from that peer.
Right, so, yeah, just to caveat, right, it's not necessarily wrong. I mean, if we want to encrypt everything, that's fine. It's just then you can't have different policies.
Oh, but you can actually. Because it's just a network interface, this is all controlled by the ordinary routing tools you already know about. So if you want to direct certain traffic to the WireGuard interface, then you just do that with route. And if you don't, then you direct it elsewhere.
Yeah, sorry, I'm misspeaking. It depends on the crypto policies that you have, which, by the way, I love the fact that you don't allow 190x, 300 cipher suites, right? So just limiting them is a really great idea. But I'll take that offline with you. But the one thing that really caught me was that you also said that the initiator must know who it is sending to, right? So you have to have an a priori trust relationship. But how do you actually establish that?
Right, so this question I explicitly place outside of WireGuard. You exchange public keys in the same way that everyone already does with SSH somehow. And then if you want to make this complicated for a big organization, then you build something on top. Maybe you use the existing certificate system you have, maybe you build something new. But the important thing here is that the key distribution problem isn't part of the same layer as the basic secure tunnel.